So in the last section, we have seen that the operations on divergent sequences. So we have seen summation, subtraction, product and quotient of convergent sequences, and which is comes out to be a convergent sequence again. Now let us see some operations on those divergent sequences. Before going to see the operations on these divergent sequences, observe some things from these divergent sequences. We have seen that the addition of two convergent sequences is again a convergent sequence. Likewise, subtraction of two convergent sequence is again a convergent sequence. Similarly, the multiplication or a product of two convergent sequence or quotient of two convergent sequences is again a convergent sequence. So let us see some example. Also, if sequence Sn is divergent, right, then sequence of minus of Sn is also divergent. Right, both the sequences are divergent, but their addition, their sum, Sn plus minus of Sn, so is the constant sequence of 0, and it is comes out to be a convergent sequence, right? So it is some meaningful observation. Similarly, if we consider some other example, sequence Sn to be a minus 1 raised to n, right? And if we consider, call it as some sequence un, which is to be Sn square, and then it is what it will be, sequence minus 1 raised to n, its square, so it will be raised to 2 times n, and it will be a constant sequence of 1, and it is a convergent sequence. Convergent or not divergent. Similarly, this sequence is also a not divergent. It means it is convergent. So these are some examples that addition or multiplication of two divergent sequence need not to be a divergent sequence. It can come out to be a divergent convergent sequence. So let us see a theorem in which case the operation on divergent sequence will produce again a divergent sequence. So few theorems are there. So theorem 1 is, if sequence Sn and sequence Tn are sequences of real numbers, that diverge to infinity. That means those are sequences which diverges to plus infinity. Then so do their sum and product. That means if the two sequences are divergent to plus infinity, in this case their sum and product will also be a divergent sequence, that is sequence Sn plus Tn and sequence Sn into Tn diverges to infinity. Right, so this is the case that Sn and Tn both should converge to both should diverge to plus infinity. So let us prove this by, so suppose it is given that Sn Tn are sequences of real number that diverges to plus infinity. So sequence Sn Tn diverges to plus infinity. So it means that by the definition of divergent sequence, it means that for any given real number m, we can choose a positive integer n. So let me say it as n1, such that all the terms of the sequence Sn are greater than that real number m, and it is true for all n greater equal the positive integer n1. And there should also exist a positive integer n2 such that the sequence, each term of the sequence Tn is greater than some integer. So let me call it as, for simplicity, take it as 1 for all n greater equal n2. Now as Sn Tn diverges to infinity, right, for any positive integer n. So let me choose n to be a maximum of two integers, positive integers n1 and n2. n1 and n2. So then we can have the addition Sn plus Tn. So what the addition will be? As Sn is strictly greater than m for all n, Tn is greater than 1 for all n. So this addition will be greater than m plus 1 for all n greater equal the positive integer n, which is chosen to be maximum of n1 and n2. And definitely this m plus 1 will be greater than m, right, for any real number m. Similarly, so it means that is Sn plus Tn is greater than m for given positive real number m. Sn plus Tn is greater than m, and it is true for all n greater equal n. It means that it says that Sn plus Tn diverges to plus infinity, right? That means there exists a positive real number m, so that all the terms of sequence Sn plus Tn for some natural number n greater than a fixed positive integer n will diverge to plus infinity. It means that the sequence diverges to plus infinity. And what we can say about the product Sn into Tn? As Sn is greater than m, Tn is greater than 1. So definitely this product will greater than m into 1. That means m. And it should be true for all n greater equal the positive integer n. Right. So it says that for any given real number m, every term of the sequence is greater than m, and it is true for all the integers n which are greater than or equal to this positive integer n. That means after some positive integer, every term of the sequence will be strictly greater than m. So it means that this sequence diverges to plus infinity, and it is what we wish to show in this case, right? The next theorem is, if sequence Sn and Tn are sequences of real numbers, if sequence Sn diverges to infinity, and if sequence Tn is bounded That means sequence Sn is diverging to infinity and sequence Tn is bounded, and in this case also then sequence Sn plus Tn will also diverge to infinity, right? So how to prove this? So the proof is that what is given? Sn Tn are sequences of real number. Sn diverges to plus infinity and the sequence Tn is bounded. So let sequence Sn diverges to infinity and sequence Tn is bounded sequences. Is bounded sequence. So as it is a bounded sequence means therefore there exists some real number, let me call it as q, positive real number, such that absolute value of every term of the sequence is bounded, that means less than or equal to this positive real number q, and it is true for all positive integers n, right? Also it is given that sequence Sn diverges to infinity. So Sn diverges to infinity. So by the definition of divergent sequence for given positive real number m, we can choose some large positive integer n such that the nth term of the sequence is greater than this some positive real number m, and it is true for all n greater equal this large n we have chosen to be, after which every term of the sequence is greater than the real number m. So therefore then for all n greater equal n, we can say that Sn plus Tn, can we compare these two things, Sn plus Tn and Sn minus modulus or absolute value of Tn? This is Sn adding something, it may be positive negative, and this is Sn subtracting something, and it is definitely subtracting positive thing. So this thing will be less, right? And as we have this thing, Sn is strictly greater than m and Tn is Tn is less equal q. So minus of Tn will be greater equal minus q, right? So it is m minus q, and for simplicity it is also sufficient, right? It is also sufficient, but for simplicity we chosen for this given m, we chosen this Sn to be greater than m plus q. It is for simplicity only, so that this q minus q get vanish, and now we get that every term of this sequence is strictly greater than a positive real number m, and it is true for all n greater equal n, right? So it means that is for given m greater than 0, the sequence Sn plus Tn is strictly greater than m, and it is true for all n greater equal n. It means that every term of the sequence after some large n is strictly greater than this large positive real number m. It means that this sequence Sn plus Tn is diverges to infinity, right? The next one is a corollary, and it is something same like that. Suppose sequence Sn diverges to infinity, and if sequence Tn converges then sequence Sn plus Tn also diverges to infinity. Right? So, and how to prove this corollary? As it is corollary, so it is depend on some standard result or a theorem, right? So it says that I will not provide the whole proof, but I will suggest something. Sn diverges to plus infinity and sequence Tn is convergent, right? And we have seen that the result, the theorem, that every convergent sequence is bounded. So every convergent sequence is bounded. So as sequence Tn is convergent, so the sequence Tn is bounded. And so it is now, it is exactly similar to the previous theorem. So therefore, by previous theorem, that Sn is a sequence which is diverges to infinity, and Tn is a sequence which is convergent, that means bounded. And now by the previous theorem, Sn plus Tn diverges to plus infinity, right? So let us move to the next section. We have completed this section number 8, 2.8, which is operations on divergent sequences. And now we move to our next section, which is section 2.9. So is the next section, section 2.9. It is limit superior and limit inferior. Limit superior and limit inferior. So roughly this limit superior and limit inferior, it means what? Limit superior means the sequence, the measure of sequence, that means how big sequence Sn can be when n is very large. And limit inferior can be a measure of sequence Sn, so that how small sequence Sn can be when n is very large. So let's see some discussion. So consider a sequence Sn and is bounded above. So then what happens? Every term of the sequence is less equal some positive real number m, and it is true for all positive integers n, right? Then as it is a bounded sequence, then for some fixed positive integer n, the set Sn, Sn plus 1, Sn plus 2, Sn plus 3 and so on is also bounded above, right? Is also bounded above. Hence, let me call it as set X. Hence, X has a least upper bound, because every subset of the sequence, every subsequence of the sequence Sn is bounded above. That means upper bound exists. So it can imply that this set or this sequence has a least upper bound. So let us call it as Mn, which is to be, we define to be a least upper bound of this sequence X. That means Sn, the terms are Sn, Sn plus 1, Sn plus 2 and so on. So my question is, what can be the relation between mn and mn plus 1? So if mn is this, so how we can say about mn plus 1? So it can be least upper bound of Sn plus 1, Sn plus 2 and so on, Sn plus 3 and so on. So the question is, can you compare Mn and Mn plus 1? So this is upper bound with this much terms and this is least upper bound with one term excluded, Sn, right? So the comparison is this Mn can be greater than or equal to Mn plus 1, right? Therefore, this sequence of least upper bound Mn is non-increasing. So as it is non-increasing, so what about the convergent of this sequence? Non-increasing. So if it can either converge or may diverge to minus infinity or may diverge to minus infinity, right? So let us see a definition. The definition is, let sequence Sn be a sequence of real numbers. Sequence of real numbers which is and is bounded above and let this Mn is equal to least upper bound of Sn, Sn plus 1 and so on. Then the definition says that if this sequence Mn converges, everywhere you have to write n where is from 1 to infinity, because as they are sequences, so it should have first term, second term and the continuity should be there. Continuity term should be there. So if this sequence converge, we define limit supremum of Sn. Supremum of Sn is to be limit of this sequence Mn. And second thing, if sequence Mn diverges to minus infinity, we write limit supremum of sequence Sn to be minus infinity when n is infinity. Right? So for example, number 1, if sequence Sn is minus 1 raised to n for positive integer n, then we know that this sequence is bounded above, right? Is bounded above. And in this case, what is Mn? That means least upper bound of nth term, n plus first term, n plus second term and so on. So it is least upper bound of minus 1 raised to n, minus 1 raised to n plus 1, minus 1 raised to n plus 2 and so on, right? So whenever the power is even, so it minus 1 raised to n will be plus 1. So the least upper bound has to be plus 1 for every n belongs to a positive integer, for every positive integer n. And hence, what will be the limit of this sequence mn, as mn will be a sequence of constant sequence, it will be even 1 comma 1 comma 1. So its limit, whatever the n, however large n is, its limit will be 1. So by the definition of limit supremum, sequence mn is convergent. Why? Since our sequence mn will be a sequence 1 1 1, and definitely it is a convergent sequence. So if sequence mn converges, then by the definition of limit supremum, it is defined that limit supremum of sequence Sn is to be a limit of this sequence of least upper bound, right? Therefore, limit of supremum of Sn is limit of supremum of minus 1 raised to n is to be limit of this sequence of least upper bound of sequence Sn, however large the n is, and it is 1, right? Second example, if sequence Sn is 1 minus 1 1 minus 2 1 minus 3 1 minus 4 and continued. So what is mn again? So it is 1, then minus 1, then again 1, then minus 2, again 1, then minus 3, again 1, then minus 4, then again 1, minus 5, continuously like this. So every term the negative numbers are increasing. The positive number is 1, which is appearing after each negative number. The negative numbers are increasing, right? So mn is least upper bound of Sn plus 1. So it does not affect the list of upper bound, because the everywhere whatever the subset you choose from this sequence or subsequence we choose from this sequence, the least upper bound is always 1. So the sequence mn is 1 comma 1 comma 1. So again sequence mn is 1 for every n belongs to I, or positive integer n. And definitely similarly as above example, limit of supremum Sn, which is limit of sequence Sn, however large n is, it is also again 1. So similarly, if we consider as next example, if we consider sequence Sn to be minus n for positive integer n, then now the least upper bound mn, which is least upper bound of Sn, Sn plus 1, Sn plus 2 and so on. So what is the least upper bound? Definitely minus n is the largest, then minus n plus 1 is the largest if we consider mn plus 1. If we consider mn plus 2, then minus of n plus 2 will be the upper bound. And then what is the least upper bound? So it has to be this first term everywhere. If we consider mn plus 1, so the least upper bound will be minus of n plus 1 continuously by this way. Hence, and by the definition of supremum, as it is a sequence which diverges to minus infinity, right? So by the definition, don't use the definition. Hence, sequence mn, as n is very large, it diverges to minus infinity, and so limit supremum of this sequence Sn for large n is limit supremum of sequence Sn, which is minus n for large n, is minus infinity. Right? So the next thing is definition. And the definition is that if Sn is a sequence of real numbers that is not bounded above, then we write limit supremum of sequence Sn for large n to be infinity. That means a sequence Sn which is not bounded above will also can diverge to infinity, and the limit supremum is definitely infinity. Right? So for example, if we consider sequence Sn to be n for positive integer n, so then it is sequence of real numbers, and sequence Sn, which is sequence n for positive integer I, is not bounded above, right? Whatever the sub sequence we consider, so it is not bounded above. The upper bound does not exist. As the upper bound does not exist, therefore its limit supremum of Sn for large n is limit supremum of this sequence n is infinity.